Yes, thank you for inviting me here. And my name is Henning Schmidt, and I come from Stockholm University. So we continue the session here. I'm not going to cure cancer or count flapping mosquitoes. I'm only going to talk about a single machine, the DESIREE storage ring in Sweden. And I have one slide that actually shows some results where we are using light. So I'll wake you up when I come to that one. So this is the outline of the presentation. So I will tell you first what is DESIREE, and then I will show a little bit of what we have done in terms of results. And then I hope that later today, the account stuff will show something more. I don't know that, but I'm working. Yes. And then in the end, I will try to encourage those who might be interested in becoming users with us. So what is DESIREE? Here's an outline of our laboratory. If you become a user, the most important part is the control room. Here's the couch where you can sleep during night shifts. And here is the coffee machine. Scientifically, the more interesting part is down here. So as the name reveals, DESIREE is a double electrostatic ion ring experiment. So as you might have guessed, we have two storage rings. And those are in this box here. And to get an idea of the size, you see this is 1 meter here in this scale. So the box here is 4 meters long, 4.5. So it's not that big. And so we can inject ions from, oh, something wrong? No, I want to put it full screen, but that doesn't work. So. Okay, that's okay. Then I can see myself. So inside here, we have two electrostatic ion storage rings, and we can produce ions in different ion sources and transport them to the rings. And the ions move with kilo-electron volt kinetic energies. And that's important, something we often forget to mention, because this is what makes us able to detect individual particles when they, for different reasons, fall out of the rings. If we take off the lid, we can have a quick look inside. You recognize the structure of the two storage rings here. And they are mounted together in this aluminum vacuum vessel that can be cooled down to 13 Kelvin. As we learned earlier today, vacuum is a good insulator. So we make use of that. So this is a separate vacuum chamber surrounded by a copper screen at a somewhat higher temperature. And then everything is wrapped in super insulation inside this steel box for the main vacuum chamber. This means that because it's so cold, we can have a very good vacuum in there, which in turn means that the ions can circulate for a very long time. So important aspects of DESIREE is that it's electrostatic. That is an advantage if you want to study molecules, heavy molecules, because we're not dependent on what mass we are storing. It also, in atomic physics, is important that some atomic physics done in magnetic storage rings suffer from mixing of fine structure levels. It's cryogenic, as I mentioned, so that means that we have an extremely good vacuum. So this corresponds to something like 10 to minus 14 millibar. And that means we can store these very fragile, for example, anions, KeV energies for up to an hour. And we can store them and wait for them to cool so that we have, for example, molecules in the lowest states so that we have control of the internal degrees of freedom. And also this long lifetime makes us able to actually manipulate the ions with lasers before we make the collisions. And finally, it's a double ring system, which makes it possible for us to study process where positive and negative ions interact with each other. and to do so at low and well-controlled center mass energies. So, I'm not only a scientist, I'm also an administrator, so I like to show this picture so you can see that we are producing more and more results from this all the time. You don't have to look at the numbers on the y-axis, just the trend. And I've sorted them here into results from single ring experiments, the blue ones, when we do experiments where we just make use of the fact we can store the ions for a long time and interact with lasers, for example. For example, the kind of thing that we talk about. And the red ones are then actually from making use of the double ring, which is what I'll focus on here. So we naturally divide our scientific output into two categories, those that use double rings and those that don't. And I don't have time to talk about this part, so we stick to the double ring experiments. And of course, the process that's obvious to study, and the reason why we built DESIREE in the form it has, is that we want to study the process where you exchange charge between two charged particles and form two neutral ones, so mutual neutralization. Usually it's atomic systems, so what's happening is that an electron goes from an anion to a cation and produce two neutrals. Here's an example of molecular curves for the molecule lithium H. And this is what we need to consider if we want to consider the mutual neutralization of lithium plus with H minus. Then we have to consider potential energy curves like these. The line that I put in here corresponds to the energy that you have if you have a it only works for a while. Okay, maybe this one. Okay, thank you. So this line corresponds to the energy of the ion pair, lithium plus and H minus. And then what happens when the two approach each other is that you come in along this curve. You can almost see this 1 over R here comes from the Coulomb attraction. And then when you come closer, you cross the levels that correspond to forming the neutral lithium in different quantum states together with a hydrogen ground state. So what can happen is that you come to such a crossing and there's a certain probability that you skip to the other curve and then you come out like this. So if you do it at this point, you come out in 3p or 3d. We cannot resolve these two in this case in our experiment. And if you do it in here, you come out in 3s. So what we want to do is to do a measurement where we measure the difference of these energies and see what actually happens here. You start with this amount of energy, and then you come out with and have lost some energy. So you have lost some electronic energy. And that can only go into one. There's only one available degree of freedom here, and this is the motion of the two. So this turns into kinetic energy. So there's a small explosion happening here. They approach each other slowly, and then they go fast away. So if we measure how far they have moved apart a certain time after the reaction happened, then we can tell which of these actually happened. So this is a distribution of distances that we measure a certain time after this reaction has happened. So how do we do that? That we do in the storage ring. So we have, in this case, stored lithium, and we chose D minus. I'll come back to that. And they are then stored at energies such that the D minus moves with a higher velocity than the lithium. If we look closer on this central part, we see that there are actually 7 drift tubes here. And what we did in the experiment is we put 3 of those on a voltage that slowed down the D minus and accelerated the lithium plus so that they have the same velocity in this small part. This way, we can then measure the arrival time differences of pairs of neutrals arriving at the detector over here. Oh, That was actually on this computer. So this was officially not my fault. Can I continue? Okay. So anyway, of course, we cannot tell these ions where to react. So there will be some mutual neutralization taking place here and here. Those are not the ones we're interested in because they happen at very high energies for what we are interested in here. But the good thing is that if it happens, the time between the two products is quite high. It's several hundred nanoseconds. So they come out here, so far away from the ones we are interested in, which are the ones that happen at very low energies, and they give this distribution in here. So out here, the position in time is determined by where along the line this happened, but here it's actually dominated by the kinetic energy release inside in the actual process. So the good news is that this detector measures not only the time of arrival, it also measures the positions of these ions, these neutrons, sorry. So from that, we can construct the actual distance in 3 dimensions after a certain time. And that is then determined by the kinetic energy release. And therefore, we can get this nice spectrum here where we very clearly see for every event if we're producing the lithium in the 3s or in one of the 3p and 3d. And we also see, by the way, that we don't form any other quantum states of lithium. So this was a description of that kind of experiment. We have done that for several systems: lithium, sodium, magnesium. And the motivation for these kind of studies comes from astronomy, because when you look at a star and you see some absorption feature in your spectrum, you see some dip in the intensity, that tells you that this star contains, for example, lithium, sodium, magnesium. But if you want to know how much of it is there, you need to know in detail the quantum state distribution in the stellar atmosphere. And that is not given just by a Boltzmann factor and knowing the temperature. You have to know the actual microscopic processes that take place there. And one important such process is mutual neutralization. So we need these measurements to confirm the theories or to test the theories such that the astronomers can know how much lithium is in the universe, how much magnesium, sodium, etc. So just one example, this is magnesium, where we did the mutual neutralization. Now we're using D minus. I know the stars contain H minus, but I'll come back. So what we have here is now a more complex situation from the one I showed you with lithium, because there are more states involved. But what we do is we measure such a distribution, and then we make a fit where we have a set of basis functions. So we fit the best linear combination of these basis functions. And those are from simulations of the actual experiment, assuming just one of the channels at the time. And from that, we can reduce the branching fractions going into all these different levels. And that we can then, the way then to compare to theory is to take just, instead of the fitted branching ratios, we take the theoretical branching ratios. And the red curve here is the one that everyone was using. So it turned out then when we published it, because the more modern, well, not more modern, but the newer theory by Paul Barklem, who is part of the collaboration, gave very good agreement with the experiment, while the more mathematically based, more full quantum mechanical, if you like, calculations were off by quite a bit. And it turns out that there are actually some basis functions that should have been included in this calculation that were not there. It also turned out that there was another actually better calculation around that we missed when we published this, but let's not go into that. But that was just one example of like this. Now, I said several times that we use deuterium instead of hydrogen, and to test how good or bad that is. Yeah, we are not related, by the way. It's a PhD student who's doing this. She measured with normal hydrogen. Instead, when we have improved our experiment a little bit, we could do that. And you see that this distribution, now it's not distance here anymore, it's directly kinetic energy release, so we can directly compare the two different experiments. And you see that the balance between the 3s and the two other states has shifted because of the different isotopes. And here is a compilation of the data we have on this system, where the red points are with normal hydrogen and the blue ones are with deuterium. And you see this difference here. This is now plotted. What's plotted here is the 3s branching fraction, so the part that goes into that particular level, and as a function of the collision energy in EV here, so we can go down to around 100 millieV. And you see this difference that was also illustrated in the previous picture. And this also sort of made our theory friends more enthusiastic about this. There was a theoretical description from Croft in 1999, where they used the quantum scattering method to describe also the heavy particles in the collision. And that was then repeated now by Paul Barklem, who's part of our collaboration, and produces these two curves here, where the blue is deuterium and the red is normal hydrogen. And then you can see all these wiggles here, and they now come from Stückelberg oscillations. So if you come in like this and come out on this one, you can do this two ways. And now, pardon this, I just made that this morning, this drawing. So you go either this way, or you go down here. And of course, in reality, in quantum mechanics, you do both, and then the amplitudes will have to be added, and sometimes you get constructive and sometimes destructive interference, and that explains these wiggles. Unfortunately, we cannot quite measure those here. So, there are several other examples of systems we have looked at, all the way up to fullerenes with fullerenes for mutual neutralization. The example I wanted to show you here now is the one that actually uses a laser. So pay attention. There's not so much photons in this talk, I realized. So the idea is we consider mutual neutralization with sodium plus and silicon minus. And this system is only chosen to demonstrate one of the aims of the whole project, that we want to demonstrate that first that we can manipulate the quantum states of the ions in our beams, and then do experiments with those. And the simplest way to do this that we could think of is to inject silicon minus, which has about, the way we produce the ions, we have about 3% of those in the doublet D metastable level. And then we have a laser here that we can use or not use. And the laser wavelength is chosen such that we can photo-detach the ions that happen to be in the excited states, but not those in the ground state. So it's around 1,000 nanometer. And then the process is this one, sodium plus and silicon minus. And so if you look at from the perspective of the electron, it's first found over here, let's say in the ground state. And then we calculated where would it end up over here, and found that only one state is actually active. And if we are in the metastable state, there are 3 final states active. And so if we do the measurement, and this is just a couple of weeks old, so it's very raw data, so sorry for that. You see that this big peak corresponds to being in the ground state of the silicon minus to start with, and forming the 3p in sodium. But then this small peak on the side corresponds to some of these. And that we can then make go away by, so when we shine the laser, we see this peak is strongly reduced. So we have for the first time demonstrated that we actually manipulate the ions for such a merge beam experiment. We've done other experiments where we manipulate the beams, but I leave that to Dark, I hope.
Yeah.
Yeah. So as I told you, there was no time for the second part of the talk.
Yeah.
So, and the chairman is already standing. So I will just end by informing you that if you would be interested in doing an experiment, you think you have an idea, something that your research could benefit from this kind of storage ring, you can contact us, and you can even apply for beam times. They come every 6 months. You don't have to.
Oh, this is already trained a little bit.
And so I did all this myself, of course, but if something went wrong, it's one of these people who were to blame. And these are some of the people based in Sweden who are either working at DESIREE, running the experiment, or coming as users. Then we have a lot of international users, of course, from famous places like Latvia, and Austria, and Latvia, and Italy, and France, and Latvia, and Norway, and Latvia, and the United States. Thank you for your attention.